morning, students. In today's class we shall be discussing about inverse of a matrix. Inverse of a matrix can be found only if the matrix is a square matrix. So whenever we say inverse of a matrix, we actually mean to say inverse of a square matrix. So if A is a square matrix of order n, and if B is another matrix such that matrix A multiplied by matrix B is an identity matrix which is same as the product of B and A, then the matrix A is said to be invertible and matrix B is called the inverse of matrix A. Because A is an invertible matrix, so B is called inverse of A, so A inverse is this. So the inverse of A is represented symbolically like this. Read it as inverse of A, which is equal to B. If we substitute this expression in equation 1, then we can write down A into A inverse, which is equal to I, which is equal to A inverse into A. So whenever a matrix is multiplied by its inverse, or an inverse matrix is multiplied by the initial square matrix, the two products are equal and the resultant is an identity matrix of the same order. Here you must have also noticed that we are writing AB is equal to BA, although we know matrix multiplication is not commutative. This is a special equation where the product is, matrices are commutative, the matrix multiplication is commutative, and the product is equal to the identity matrix. If this condition holds true, only in that case B is called the inverse of A. We can read the equation other way also. We can say that B is also an invertible matrix and A is called the inverse of matrix B. So in that case, A is called the inverse of B, and the equation can again be written as B inverse into B, which is identity matrix, which is B into B inverse. So if we have AB is equal to BA, which is equal to identity matrix, then inverse of A is B and the matrix B has its inverse, which is matrix A. What exactly do we mean by inverse of a matrix? So for this, let us consider a matrix equation. Matrices A and B are square matrices of same order so that multiplication is possible, and the resultant is a matrix C of the same order. If we want to shift this matrix B to the other side, simple algebra tells us that the transportation can take place this way. This equation can be written as A into C into B inverse, or matrix A can be written as B inverse into C. Since we know that matrix multiplication is not commutative, so which is the true expression for matrix A? So here we have to see that we are basically dividing matrices. So whenever we want to divide a matrix by another matrix, we call it inverse of a matrix. We multiply a matrix by its inverse. So we are trying to find out which of these equations is the right equation. So we'll go back to the original equation. AB is equal to C, and post multiply the equation by a matrix B inverse. So we get matrix AB multiplied by B inverse, which is C into B inverse. Because we know matrix multiplication is associative, so A into B, B inverse is CB inverse. We have just now seen that a matrix multiplied by its inverse is identity matrix, and identity matrix multiplied by any matrix is the matrix itself. So finally we discover that matrix A is C into B inverse. This is the right equation. This is not the right equation. So it is important to remember that inverse of a matrix can be found, but which of these equations is correct? We have to understand that because matrix multiplication is not commutative. Next, we'll consider an important theorem given in the textbook. If the inverse of a square matrix exists, then it is unique. This condition is already given to us. The inverse of a matrix exists, a square matrix. So we have to show that the inverse obtained is a unique matrix. Let A be a square matrix of order n, and let B and C be two matrices which are inverses of matrix A. Now since B is inverse of A, means that A into B is I, which is B into A. Likewise, since C is inverse of matrix A, that means A into C is equal to identity matrix, which is C into A. Let's start from the first equation. AB is equal to I. So pre-multiply the equation by matrix C. We get C into AB is C into I. Because matrix multiplication is associative, so CA into B is equal to C. Any matrix multiplied by identity matrix is the matrix itself. And CA, you can see, is identity matrix, replacing IB is equal to C. Again, I into B matrix is matrix B, which is equal to matrix C. So if we start with the concept that B and C are two inverses, we end up with the result that B and C matrices are the same matrices. Hence, we can easily say that a square matrix will have exactly one inverse, if at all it exists. So since we know what is inverse of a matrix, we'll move on to the next step where we'll try to find out the inverse of a square matrix. So inverse of a square matrix can be found in two ways. One of the methods is using elementary operations. And the second method is using a formula. This formula is given in the next lesson, that is determinants. So this method of finding out the inverse we will study in the next lesson. So this is what we are not discussing right now. We are focusing on one of the methods, that is using elementary operations. There are two kinds of elementary operations defined for a matrix: row operations and column operations. There are three kinds of row operations and three kinds of column operations possible. Let us understand these operations with an example. So I'll start with row operations. If we have a square matrix of this kind, then one of the kind of row operations, because there are two rows, we'll represent these rows as R1 and R2. So the first kind of row operation is written this way, which means that rows R1 and R2 interchange. If it interchanges, the matrix is, the second row becomes first row, the first row becomes the second row. So this is a new matrix obtained after performing this operation. This operation allows us to interchange rows of a matrix. The second kind of operation is, because there are two rows, I'm choosing row 1. Some changes in the elements of row 1 can be made this way by multiplying the elements of row 1 by some scalar. I am taking this scalar to be suppose 2. That means the new row will be 2 times the initial row. This was our initial matrix. So now the new matrix that we get here is only the first row changes. Each element gets multiplied by 2. There is no change in the second row of the matrix. So here we have got two matrices where we have made some changes in the rows using two operations. First operation where rows can interchange. Second operation where one row, the elements of one row can be changed by multiplying its elements by a non-zero scalar. The third kind of row operation possible is, since I am making changes in row 1 only, so I am writing this way. This way. What it means is that initially we have row 1. What are we adding to it? Corresponding elements of twice of row 2. The new row obtained is row 1. So let us see here, I am writing the matrix again. This is the initial square matrix. If we perform this operation, this row operation on this matrix, the elements of row 1 will change. The operation is this, adding corresponding elements. So the first element 1 plus twice of second 2 times the corresponding element of row 2. So the element obtained here is 7. Next, row 1 element is 2 plus 2 times this element, which is 4. So that gives us 10. So the first row has changed by adding twice of corresponding elements of the second row. So this way you can see 3 row operations are possible. 2 rows can be interchanged. A row can be expressed as lambda times the elements of the same row, or row 1 or row 2 can be expressed as R1 plus 2R2. In the third operation, you have to ensure that if the operation is written like this, then the operation is wrong, because the row which is written here is to be written here. The row which is written here is basically the reference row. What are we doing? Which row are we changing? This row. How are we changing this row? By adding or subtracting something to it, to the corresponding elements. And finally, the second row can be obtained. So the correct operation would be like this. Row 2, a new row 2 can be obtained if to the initial row 2 we add twice of R1, or row 1 in new row R1 can be obtained if to the initial row, we from each element of initial row, suppose we subtract 3 by 4 times row 2. This way. An operation of the kind R1 is R1 plus 2 is not possible, because 2 is a scalar quantity. A scalar quantity directly cannot be added to a row. So here it has to be, say, twice of R2. So we have discussed row operations. Next, let's move on to find out the column operations. There are three kinds of column operations also possible. The first column operation, these are all similar to row operations. I've considered a square matrix of order 2. So there are two columns and columns can be interchanged. If this is done, the matrix that we obtain here is column 1 will become column 2 and column 2 becomes column 1. So the new matrix obtained is this. The second column operation which is possible is lambda times elements of C1 multiplied will give us the new column C1. So here again I am taking lambda to be -3. So the new matrix that we obtain, since we are changing column 1, so the column 1 elements are multiplied by -3. The new column elements that we obtain are -3 and -9. The second column elements remain the same. The third operation, changes in column 1 can be made this way. This is the new column C1 which is obtained by adding to the elements of initial column C1 corresponding elements of C2. So the matrix A that we considered initially was this. After performing this column operation, the row C1 will change. Elements are 1 plus 2, 3, 3 plus 4, 7. The second column does not change at all. So here again, if we write down an operation of this kind, this basically means that elements of the column C2 are changed. If elements of column C2 are changed, we cannot obtain column 1. So this has to be column 2. All we have to remember is the row or column that we mentioned here is mentioned here immediately after the arrow. An operation of this kind is also a valid operation, because here what we are doing is a new column C1 is obtained if twice of C1 we are adding corresponding elements of C2. So this way 3 column operations are possible, 3 row operations are possible, and these are called the elementary operations or elementary transformations. And using these row and column operations, we shall be finding out the inverse of a 2 by 2 and a 3 by 3 matrix in the next class.